I'm Valentin. I'm a software engineer here at Google, and I'm working on Apache Beam, mostly on Python SDK, and also work on Cloud Data Flow. And today I would like to share some of the debugging techniques that I learned over time from debugging customer issues, which is part of my job here. There is a link to the slides, and with that, let's get started. So how a pipeline might fail? Well, ideally, the pipeline does not fail. In less ideal case, the pipeline fails, but produces a clear and actionable error that tells you what to do to avoid the failure. And in an unfortunate case, the pipeline fails, and there is no clear or actionable error, and you're wondering what's going on here. This is the type of the errors that we will be talking about today. In a very, very, very simplified picture, you could say that the processing happens in the following manner, where there is a runner and there is the SDK, and the runner tells the SDK, oh, here is a bunch of elements, I want you to process it, and then the SDK instantiates the do function and calls the process method on each of the elements, computes certain results, and eventually tells the runner, I'm done. And this processing can be happening inside the process, and the process might be wrapped in some other abstraction, like a Docker container, which might also be inside the worker VM. The points of this talk that I'm going to be discussing is what are the clues that we can find from observing the SDK harness process from the outside when the SDK itself does not tell us what's wrong and the runner does not tell us what's wrong. And the examples that I'll be discussing here are some pipelines or some issues that I happen to debug some. With that, first case, identifying a memory leak. So a few months ago, we noticed that in one of the customer issues that there was a pipeline, and after the user upgraded the SDK, they observed that the RAM usage in the pipeline on the workers keeps growing as the pipeline keeps running. And that's one example where there's clearly a problem, but you don't see the exact root cause where the problem comes from. And we clearly need to fix it. And we knew that it correlates with the updates that we made in our SDK. So what can we do? Well, one of the ideas was, can we instrument the SDK harness process with a profiler? And can we do some analysis on maybe the heap dumps, or basically see where is the memory being allocated? How can we find where we are leaking the memory? And the considerations for choosing a profiler, well, it would be good if it can help us detect the leak, and it does not require the SDK process to finish before we can analyze the results from the profile. It's aware of the SDK language, in which case it's Python, and generally easy to use and still maintained. One reason why we could not use the instrumentation already available in Beam SDK was that when we analyze the heap dumps that Beam can collect, we only can see the Python portion of the heap dump, and we did not see the leak in the Python heap. So it was clearly that the leak was somewhere outside in the native allocations, and we were not able to detect that with Beam itself. So after looking at different memory profilers, we had some success with Memory, which is a profiling utility developed in Bloomberg. It's very easy to use, and I would highly recommend it whenever you need to do some memory profiling. It works great. It's documented and supported, and we were able to use it to detect the leak we had. So what do we need to do to instrument the Beam SDK container with a profiler? Well, Beam is open source, and the SDK container is also open source. So it's easy. Well, it's not super easy, but it's possible to do it. And what it takes we have a container definition, and it's roughly like this. We have a base Linux image with Python interpreter. We install some Beam SDK dependencies in that image, and we have an entry point that launches the SDK. And then the entry point does a few things, like downloads dependencies, creates the virtual environment, and launches the SDK harness. To add the profiler in the picture, we needed to modify a few things. First, we need to install the profiler, and then instead of launching the Python interpreter directly, I would have the profiler launch the interpreter. And in this scenario, the memory profiles would be collected during the time when the workers are running. And one convenient thing here is that we did not have to wait for the SDK process to stop before we can analyze the profiles. Some of the profilers I looked at require the process to finish. It's not the case with memory. So yeah, and then if you can reproduce your leak in a local runner, it's even much simpler. So you can, if you have a simple pipeline that reproduces a leak, you can launch the direct runner from under the profiler and collect the profiles. And then to give a taste what the profiles look like. So there are several different reports that you can create with memory. There is the flame graph report and the table report. It was much easier to see the leak on the table report. It basically pinpointed the location in the Beam code where the memory was allocated. And there is another mode in memory where you can also trace allocation in the native code. And as it turned out, the leak was caused in one of our dependent packages and was identified and fixed. So another scenario where you might have a problem but not have an error is stuckness. And this is another case I would like to discuss, which is also comes from something we have seen in production. And the symptoms looks like so. You have a pipeline, it's stuck, the watermarks are growing, but we do not see what is actually happening on the workers. So there is a mechanism in Beam where you can knock on the SDK harness and say, hey, what are you doing? And the SDK harness can say, oh, I'm processing these bundles. But when the runner, in this case Dataflow, did this, it got a response that, oh, I cannot retrieve any status information. And then eventually the SDK will just terminate, or runner would terminate the SDK. So something goes wrong, SDK gets stuck, but we have no idea what causes the stuckness. What can we do? Well, this is a small description of this, what the status info is. And if you are curious, there is a document that describes it. The status info collects this kind of debugging information, but in our case, it was not available. It's supposed to have the thread dump that tells you exactly where the SDK is stuck, but it didn't produce anything. So given that we know that the SDK harness serves the status in a background thread, one idea we had, or the hypothesis, could it possibly be that some other thread just holds the global interpreter lock indefinitely, and the thread that is supposed to collect the SDK status information never gets to run? Well, we can find it. So the plan, how to find that information was like so. Find a reproduction in a running pipeline. And we were fortunate in this case because we had a test that also hit the same issue as reported by one of our customers. So once we have the reproduction, the next step is to find the worker that is stuck and then locate the SDK process on that worker and then inspect it for the stuck frames. So, okay, you have the pipeline. How do you find what worker is stuck? With Dataflow Runner, we actually have an execution details page that tells you whenever we observe certain kinds of stuckness, and it can tell you what worker is stuck, and you can continue your investigation from that point. And then once we identified the worker and the stuckness was happening at runtime, we could log into the worker VM, find the containers that's running the Python SDK harness, and then use another tool that would inspect the process that runs the SDK harness and the process that is stuck. To do that, we had to find the running container and get a shell inside that container that runs in privilege mode so that the ptrace syscalls are possible. And then what tool we can use to inspect the process? Well, turns out Bloomberg has another fancy tool that works great called PyStack. And yeah, so once we get a shell in the container, we can run the PyStack tool to inspect the running SDK harness process, and you can produce a report of what threads you're running in the process and which of those threads currently has the global interpreter lock. And it also can show the native stack traces, so Python and C++ stack traces in the same report. And from this report, we could again find that the problem was in one of our dependencies, and it was root cause and fixed in the next releases. You can also do similar inspections with GGB, although the user experience might have a higher learning curve, steeper learning curve. Okay, and then one other case that we encountered sometimes is the segmentation fault. What does that look like? Well, sometimes you have a running pipeline, and especially if your pipeline uses extensions, sometimes the extensions crash the Python process and the SDK does not get to actually report the error to the runner because it just crashes. And then there is this line saying that, oh, there is a segmentation fault, and the core has been dumped, but then can we actually access that core and inspect it? Well, it depends on your runner, and in case of Dataflow, it's actually not easy to access that core file. It was not possible, but we made recently some changes to make it possible to get those core files. The reason is that the default core pattern, how we save the core files on the Dataflow workers, is not compatible with Beam SDK containers, and we need to customize the core pattern. And to do that, we introduced a new experiment that is actually not yet fully in production, but it will be in a couple of weeks. And using that experiment, you can configure your SDK containers to save the core pattern in a particular location, and then you can instrument your custom Docker container to save the core files to a GCS bucket, for example, and analyze them later when you collect the core files after the crashes. And again, you can analyze the core files with debugging tools such as PyStack or GGB. When analyzing the memory profiles or analyzing the core files, it is important to create the reports in the same environment where they were generated. So either on the same worker as it's running or replicating another Docker container from the same image so that the symbols from the shared libraries that were collected while the process was running match the libraries that are available when the report is being created. So for more information, here are some links. We have some documentation about debugging the memory leaks or investigating the process stuckness, and I highly recommend to check out the tools that I mentioned, Memory and PyStack. They're great and well documented and easy to use. And there is a link to the slides. Final thoughts is these steps, while possible, are somewhat involved, and I don't expect most users to do them. And I think the next step here is to make Beam runners surface this kind of debugging information easier so that users don't have to go down these rabbit holes to extract these clues when things go wrong. And that's it.